Hello and good morning, everyone. My name is Amani Karchoud, and I'm the Technical Product Marketing Manager at SYSGO. And today I'll present to you the integrated RTOS and Hypervisor ecosystem for MPU and MMU-based processors. In SYSGO, we do have a number of products that have been designed to meet the highest requirements when it comes to safety and security, including PikeOS, first released in 2003, which is a hypervisor and a hard real-time operating system based on separation kernel. Linux, our first product, an industrial Linux distribution with long-term support. And more recently, PikeOS for MPU that is compatible with lightweight systems that comes with memory protection unit, MPU only, which provides real-time partitioning for MPU architecture. In SYSGO, we drive innovation and create value for customers globally in different segments. We do have expertise allowing us to understand complex market dynamics and anticipate trends that impact our customers' business. Now moving to our flagship product, PikeOS, and here we will dive into PikeOS's fascinating architecture, and we will explore how its innovative design addresses the challenges of safety-critical systems. It's worth noting first that PikeOS uses a modular approach, allowing for seamless integration of diverse software components. This empowers the creation of customized solutions that precisely match the specific requirements and configurations of various applications. As we can see in this slide, on the lower level of PikeOS, we find the PikeOS microkernel, which consists of a generic part, a CPU architecture-dependent part called ASP or Architecture Support Package, and a platform-dependent part called PSP or Platform Support Package. On top of that, and in the user mode level, we have the PikeOS system software component, which is the first user space application launched by the PikeOS microkernel. It is responsible for initializing partitioning, inter-partition communication, and health monitoring. On top of the core operating system, there we can find different partitioners. Software partitions here are also called virtual machines because it is possible to implement a complete guest operating system inside the partition, which executes independently from other partitioners. PikeOS supports multiple guest operating systems that we refer to as personalities, including POSIX, ARINC653, Linux, Android, LinOS, PikeOS Native, and many more. PikeOS partitions showcase its capability in effectively handling mixed criticality applications. By isolating software functions, it enables different applications from safety critical to non-critical to run securely on the same platform. This makes PikeOS a reliable choice for industries requiring a balance between safety requirements and versatile application integration. And this also will allow industries to reduce the certification effort to resolve licensing issues by means of separation and also the reusage of legacy code. In this context, we are ensuring the support of mixed criticality applications by using two main security mechanisms, which are resource partitioning and time partitioning. So in resource partitioning, we are ensuring that every partition in PikeOS has its own dedicated set of resources. By doing this, we are enforcing strict isolation between partitions, preventing one partition from accessing the resources allocated to another. Here is the MMU role to enforce memory isolation that contributes to the overall resource partitioning strategy of PikeOS, preventing any unauthorized memory access between partitions. Time partitioning is also one of the security mechanisms to support mixed criticality applications. PikeOS ensures time partitioning by employing a real-time scheduler within its microkernel architecture. Each partition is allocated a specific portion of CPU time and priority, which the scheduler enforces. This guarantees that partitioners receive their allocated CPU time, preventing one partition from monopolizing resources. SYSGO has taken a significant step forward by integrating multi-core handling into their time partitioning mechanism. This advancement holds the potential to reshape the landscape of real-time operating systems, addressing the growing demands of today's complex embedded systems. Moreover, safety issues regarding to multi-core systems may arise on software and hardware level. For this, SYSGO proactively implemented solutions to address those challenges. On software application level, SYSGO has prepared all means for the user to define and implement an airworthiness architecture on the PikeOS base. On operating system level, SYSGO has implemented all safety measures in order to safely set up mixed-critical systems using resource partitioning, time partitioning, and fine-grained locking. And by the way, PikeOS is the first operating system that achieved a multi-core certification on SIL 4, which stands for the highest level of safety in the railway system. Continuing in the multi-core context, hardware may cause further interference through shared caches. Those effects can be mitigated by means of software measures like cache partitioning and cache invalidation. And when using PikeOS, customers are enabled to build CAST32 compliant systems. To understand how this is working, let's have a look at this example. Here we have two cores in the time partition window TO1, where we run a non-critical partition and an application with a high impact on the cache. Afterwards, we are doing a cache invalidation, and then we run the critical applications in parallel. And from those, we know the exact behavior, because those have been certified and investigated so they don't access the bandwidth or resources or the shared resources in an unwanted way. So we don't have any interference between those applications at runtime. In SYSGO, we do have a number of products. We have Elinos, our Linux distribution. We have PikeOS, a hard real-time operating system based on Hypervisor technology that requires the presence of MMU. And PikeOS for MPU, which is the full PikeOS API for controllers that do not have a memory management unit, MMU. This allows to have PikeOS run on systems that are way less complex and are ready for systems with single appset. And actually, space was one of the major topics that drove the development of PikeOS for MPU. Let's dive now into the main differences between MMU and MPU. MMUs, or memory management units, play a central role in managing memory in computer systems. They are responsible for tasks like translating virtual memory addresses to physical memory addresses, implementing paging mechanisms, and ensuring memory isolation. This capability is in particular useful in larger and more complex systems, where the need for efficient memory utilization and isolation of processes is so important. On the other hand, MPUs, or memory protection units, are designed with a specific focus on memory protection and access control. They allow for the creation of defined memory regions with distinct access permissions, ensuring that only authorized processes can interact with specific memory areas. This level of precision in memory protection is valuable in systems where security and controlled access are of critical concerns. While both MMUs and MPUs contribute to the system integrity, their strengths lie in different contexts. MMUs shine in larger systems where memory translation and efficient sharing between processes are essential for multitasking. On the other hand, MPUs excel in more simpler systems by prioritizing precise memory protection. When examining process handling, MMUs facilitate complex processes by enabling virtual memory and seamless memory sharing between processes. And this enhances the overall system performance and multitasking. In contrast, MPUs are well suited for simpler systems where the focus is on maintaining the security and isolation of individual processes. They achieve this by ensuring that each process remains within its allocated memory area, protecting it against unauthorized access or disruptions. Let's briefly summarize the pros and cons of the usage of MPU. So for the advantages, the usage of MPU allows for a tighter bound for worst-case execution time analysis, and thus higher time determinism. And also, MPU runs on less complex hardware and chip design. For the disadvantages of the usage of MPU, we have less flexibility on memory allocation, and the virtualization is not supported, and thus complex operating systems such as Linux cannot be executed. Let's get into the setup of MMU and MPU by separation kernel. MMU systems usually provide cache coherency and prefer SMP configurations due to higher efficiency in terms of memory usage and computing bandwidth. An SMP system can only handle cores of the same type. For example, a mixture of MMU cores and MPU cores is not possible here. On the other hand, MPU hardware typically is less complex and does not provide cache coherency amongst the cores. SMP systems are possible with caches being switched off. However, this is disregarded due to the lack of performance. So, what is PikeOS for MPU? PikeOS for MPU is a real-time operating system designed for highest level of safety and security. It has the capability to execute concurrently applications with different safety and security assurance level. And here, of course, we are supporting mixed criticality. It has spatial and time partitioning, and PikeOS for MPU shares with PikeOS the same native API, the same customer development environment, which is Codeo, the same SYSGO development and test environment, the same qualification processes, and both operating systems share about 80% of the same code. And for the existing source code that you have, you can easily port it from PikeOS to PikeOS for MPU. In this case, and due to the nature of not having an MMU, the virtual address management and the ability to run a Linux operating system, of course, is not present within PikeOS for MPU. But it has address space protection, of course, thread management and scheduling, resource management and protection with respect to resources and processing time, health monitoring, inter-partition communication and synchronization, as well as intra-partition communication and synchronization, and I/O device abstraction and access control. Also, it has AMP multi-core processor support. Since PikeOS and PikeOS for MPU have identical APIs and are running under the same development platform, Codeo, this allows simply to move tasks from one operating system to another one. And by using the same API also, we are able to reduce significantly the learning curve, as you can just apply the knowledge that you got from PikeOS. So when it comes to development, we have our own development IDE called Codeo, which is an Eclipse-based IDE. Codeo is an integrated development environment for embedded systems. It has a quick and easy target system configuration. It has templates for system configuration and application development. Its simulation target is based on QEMU. It has target system monitor and target system tracing. It is fully featured for remote debugging, and it is available for Linux and Windows hosts. As you can see in this slide, when it comes to certification, we are supporting all major safety standards. And SYSGO has a very long history in certification projects. Almost every engineer of our team has been involved in such certification projects, whether it is safety or security related. In this slide, you can see the PikeOS components and their certification state. So you can see that the microkernel is fully certifiable, which means you can provide all necessary documentation, including traceability and coverage. However, if you have your custom board, the PSP needs to be developed together with you as customer. When it comes to operating systems and certifiable APIs, we have certifiable POSIX, and of course, the PikeOS native is pre-certified. And depending on your needs, we can certify further operating systems. In addition to that, for PikeOS, we also provide a certifiable file system and a certifiable UDP stack. Another important topic when it comes to certification is the tool qualification. So basically, you can do a certification without any tools being qualified, as long as you verify your results. And if you do that on a binary basis, it is basically possible, but very, very tedious. Therefore, SYSGO has qualified the major tools, for example, the ROM image builder and the VMIT builder. The VMIT stands for the Virtual Machine Initialization Table, and it is responsible for the configuration of the virtual machines. Both of those tools read the configuration file in XML and convert it to a binary. And since those tools are qualified, you can easily do the validation on source code level, which means that you can quickly incorporate changes without doing the complete revalidation on binary level. So what also you can do with PikeOS and PikeOS for MPU is to run them in the same hardware platform. For example, today we have the Xilinx UltraScale board here, and this allows to run PikeOS implementation on the Cortex-A53 processors cores, as well as PikeOS for MPU on the Cortex-R5 cores. So now let's dive into the world of FPGA virtualization and how it benefits mixed-criticality systems. In mixed-criticality systems, various applications with different level of importance are integrated into a single hardware platform. To make this integration work effectively, we need to employ partitioning and sharing techniques. These techniques ensure that the applications are isolated from each other and can efficiently coexist on the same hardware. FPGA virtualization is a key technology in this context. It enables multiple guest operating systems to use the same reconfigurable hardware resources while maintaining isolation and performance guarantees. This approach offers several advantages for mixed criticality systems. It helps in reducing both cost and complexity by consolidating hardware resources. Additionally, it enhances resource utilization, ensuring that critical and non-critical tasks can efficiently share the available hardware. In this context, we are facing several critical challenges. Firstly, we need to ensure spatial and temporal isolation among different applications running on the same hardware. Secondly, we must effectively manage the dynamic reconfiguration of hardware resources to adapt to changing needs. And lastly, we are aiming to provide a uniform interface for accessing hardware accelerators in order to simplify development. To meet these challenges, we have a set of clear requirements. We need to support different types of guest operating systems such as Linux, real-time operating systems, or bare metal applications. Additionally, we must provide robust mechanisms for communication and synchronization among these diverse applications. And lastly, the compliance with industry standards and regulations is of utmost importance to ensure safety and reliability. One of the key techniques we employ here is space multiplexing, and this involves dividing the FPGA into regions or slots. Each of them is designated for different applications or users. This approach enables the simultaneous execution of multiple applications on the FPGA, ensuring there is no unnecessary overhead or latency. And we can achieve this through dynamic resource allocation or instruction dispatch, and as a result, enhancing the overall efficiency of the system. Another vital technique is time multiplexing. Here we switch the FPGA between different applications or users at different times. And this can be done using techniques such as partial reconfiguration or overlay architectures. Time multiplexing here allows us to make optimal use of FPGA resources, ensuring that each application or user gets its fair share of available hardware while maintaining performance and isolation. As we now came to an end of our presentation, let's try to recap the key takeaways for today. By leveraging an integrated RTOS and hypervisor ecosystem, you gain the ability to design systems compliant with CAST32A guidelines. This approach allows you to harness the power of processor cores equipped with both MMUs and MPUs simultaneously, effectively address inter-core communication challenges, and streamline development with a unified IDE and validated tools. We've also highlighted the importance of FPGA virtualization, which proves to be a valuable technique for mixed-criticality systems. It significantly enhances resource utilization and boosts throughput, making it a vital tool in modern embedded and critical applications. Looking forward, the field continues to evolve. Future directions include enhancing compatibility and interoperability among different methods and systems, elevating the security and isolation of FPGA resources, and exploring novel applications and domains that stand to benefit from the versatility of FPGA virtualization. If you reached this point of presentation, we would like to thank you for your engagement and participation today. And if you have any questions, comments, or ideas to share, please feel free to connect with us.